Good morning, grade 10. Hope you are all doing well and being safe. This is Miss Pamela Teeny giving the physics course. Today we are going to start with section 3 in chapter 19. It talks about combining electric forces. If you can all please open your books on page 690 so you can follow up with me. We already studied electric force and how we can calculate electric force. Today we are going to talk about combining electric forces. So what is the total electric force? The total electric force acting on a given charge is the sum of the individual forces between just two charges at a time, with the force between each pair of charges given by Coulomb's law. So whenever we have several charges near each other, several electric forces exist. If we need to know the sum or the total electric force acting on one charge, we add the individual charges acting on this charge and we can get the total electric force. We find each individual electric force using Coulomb's law, which we already studied. As an example of combining electric forces, consider the system shown in the figure below. Please concentrate on the yellow circle. We have three charges, Q1, Q2, and Q3. If we are talking about Q1 and we need to find the total electric force acting on Q1, we must know that two forces act on Q1. An electric force exerted from Q2 on Q1, and it is a repulsive electric force because Q2 and Q1 have the same charge. And also we have the electric force exerted by Q3 on Q1, and it is also a repulsive force. As we already stated in the previous session, that the electric force acts along the line that connects the two charges. It may be attractive or repulsive. Here it is repulsive because the three charges have the same sign, which is positive. So in this case, the total force acting on charge 1, which is F1, is the vector sum of the forces due to charge 2 and charge 3. So we have the total force acting on charge 1 is the force exerted by 2 on 1 and by charge 3 on charge 1. In order to add them here, we cannot just add the magnitudes of the forces because forces are vectors. They have magnitude and they have direction. So in order to add the forces to find the total force, we need to add them as we add vectors. So electric forces add by vector addition. Electric forces combine by vector addition to give the total force. This addition process is referred to as the superposition of forces. So we do a superposition of forces, which means we add the forces by a process called the vector addition. And I'm going to talk in details about it now. Now look at the figure in front of you where the yellow circle is, to the right. This shows the superposition of forces which I just talked about. It shows how we superpose F13, which is the force exerted by charge 3 on charge 1, and F12, which is the force exerted by charge 2 and charge 1, to find F1, which is the total force. I will explain in details how we add vectors by drawing and by calculation, which we already know from last year, but I will remind you how we do that in order to be able to find the total force acting on a charge and to understand this example more clearly. So recall vectors addition. Whenever you want to add vectors, you add them first by drawing and then by calculation. First, I'm going to talk about the drawing part. In order to add vectors by drawing, you put the tail of the second vector on the head of the first and so on. Then you draw the resultant vector from the tail of the first to the head of the last. So the head is where the arrow is and the tail is where there's no arrow. So you have to remember this rule whenever you are adding vectors by drawing. So repeat it in your head whenever you want to draw a resultant force. You say, I put the tail of the second vector on the head of the first. Then I put the tail of the third on the head of the second, etc. until all the vectors that I want to add are done. And then I draw the resultant vector, which is the total vector, from the tail of the first to the head of the last. We will see several examples. In the figure in front of you, you can see the first two examples. They are very simple because here the vectors are on the same coordinate axis. So in part 1, they both are on the x-axis, or they both are horizontal. So we have 15 newtons to the right and 5 newtons to the left. When I superpose them and I put them above each other, the resultant force is to the right. So it is in the direction of the larger vector. If 15 newtons was to the left and 5 newtons was to the right, then the resultant vector would be to the left. So the resultant vector will be in the direction of the bigger vector. So the resultant vector here is 10 newtons to the right. Now look at part 2. Also, we have two vectors that are in the same coordinate axis, which is the vertical. We have 20 newtons upwards and 3 newtons downwards. Whenever we superpose them, so we put them above each other, the resultant vector is the vector drawn from the tail of the first to the head of the last. So it is 17 newtons upwards. It is in the direction of the bigger vector, which is upwards and not downwards. If the bigger vector was downwards, then the resultant force or the resultant vector will be downwards. So we just subtract them from each other. Now in example number 3, we have one vector that is on the horizontal and one vector that is on the vertical. Here we remember the rule that I talked about. We put the tail of the second on the head of the first, and then we draw the resultant vector from the tail of the first to the head of the last. So the second vector is B. We put the tail of B on the head of A, as shown in the figure, and then I draw the resultant from the tail of A to the head of B. In number 4, I have 3 vectors, so it is more complex, but it is easy if we follow the rule. I put A, I draw it like it is, because it is the first vector. Then I bring B and I stick the tail of B to the head of A. Then I bring C and I stick the tail of C to the head of B. And the resultant vector is from the tail of the first to the head of the last, as you can see in the figure in front of you. So this is how we can find the resultant vector by drawing. Now I'm going to talk about how we can find the resultant vector by calculations. So also by calculation, we have to follow several steps in order to find the magnitude and the direction of a resultant vector. First, we find the x and y components of each vector that we need to add. Then you add the x and y components to find the x and y components of the total vector, of the resultant vector. And finally, we can find from these components the magnitude and the direction of the resultant vector. Now follow up with me so you can understand. In order to find the x and y components of a vector, we use the following equations. Rx, which is the x component, is equal to r times cosine angle. R is the magnitude of the vector and theta is the angle of the vector, the direction of the vector relative to the horizontal. Ry, which is the y component, is equal to r times sine angle. So it is the same, but the difference is that here we use sine and not cosine. R is the magnitude of the vector and theta is the angle relative to the horizontal. So in order to find the x and y components, we need to know the magnitude of the vector, the length of the vector, which are r, which is called r, and we need to know the angle, the direction relative to the horizontal. In order to find the magnitude and the direction of the resultant vector, which will be the last step, we need to use the following equations. R, which is the magnitude, is equal to radical rx squared plus ry squared. So in order to find the magnitude of the resultant vector, we use the following equation: radical x component squared and y component squared. And in order to find the direction, which is the angle of the resultant vector, we use the following equation: tangent minus 1 is into ry over rx. So tangent minus 1 into the y component over the x component. Tangent minus 1, when we want to put it on the calculator, we put shift tangent and not tangent to the power minus 1. Shift tangent, we get minus 1, and then we put the values of the y component over the x component. In order to know the angle of each vector, you follow the rules that I stated in front of you. First, if the vector is horizontal to the right, the angle is 0 degrees. If the vector is horizontal to the left, the angle is 180 degrees. If the vector is vertical and upwards, the angle is 90 degrees. And if the vector is vertical and downwards, the angle is negative 90 degrees. If the vector has an angle other than these 4 angles that I just stated, the angle will be given. So the angle is either given or it will be one of these 4 cases. Now I will give you an example of how to find the total electric force acting on a charge, and I will follow several steps that you need to memorize and follow whenever you have such an example or such a problem. The example states that we need to find the magnitude and direction of the total electric force acting on charge 2 shown in the following figure. As you can see in the figure in front of you, which will be given, charge 2 is equal to negative 6 coulombs, charge 3 is positive 5 coulombs, and charge 1 is equal to positive 3 coulombs. The distance between charge 2 and charge 3 is 0.3 meters. The distance between charge 2 and charge 1 is 0.5 meters. And charge 3 is over the horizontal by an angle of 31 degrees. In order to solve such a problem, first we need to find the magnitude of each electric force using Coulomb's law. So here in this problem, we need to find the total electric force acting on charge 2. So we need to find the magnitude of all the forces acting on charge 2. In this example, we have charge 3 exerting an electric force on charge 2, which is attractive because they are positive and negative charges. They are different charges. And charge 1 exerts also an attractive force on charge 2 because they are positive and negative. So first we find the electric force exerted by charge 1 on charge 2. It is equal to K, Coulomb's constant, times Q1 times Q2 over R squared, equal to 8.99 times 10 to the power 9 newtons dot Coulomb squared per kilogram squared, times 3 coulombs, which is the charge of Q1, and times 6 coulombs, which is the charge of Q2, over 0.5 meters squared, which is the distance between charge 2 and charge 1. The answer is 6.47 times 10 to the power 11 newtons. Now we need to find the electric force exerted by charge 3 on charge 2. It is equal to K times Q3 times Q2 over R squared, equal to 8.99 times 10 to the power 9, which is Coulomb's constant, times 5 coulombs, which is Q3, times 6 coulombs, which is Q2, over 0.3 meters squared, which is the distance between the two charges. And the answer is 2.99 times 10 to the power 12 newtons. Here I must note that we need to remember that we only use the magnitudes of the charges and not the sign. So if it is negative charge, we only put the magnitude. In the second step, we draw the vectors that represent the electric forces acting on Q2. So as you can see, the vectors that are in red in the figure in front of you. First, we have F1 on 2, which is the force exerted by charge 1 on charge 2. It is downwards and it is toward charge 1 because the force between them is attractive, because they have different charges. So charge 1 pulls charge 2 towards it. And also it is the same case for F3 on 2, because charge 3 and charge 2 have different charges, so charge 3 pulls charge 2 towards it. The difference is the directions. First, we draw the vectors along the lines that connect both charges. So F1 on 2 is parallel to the line that connects charge 2 and charge 1, and F3 on 2 is parallel to the line that connects charge 3 and charge 2. In addition, charge 3 on charge 2 is greater in magnitude than charge 1 over charge 2, as we already seen in the answers above that we calculated in the first step, and also because the distances between charge 3 and charge 2, the distance between charge 3 and charge 2 is smaller, and the magnitude of charge 3 is bigger than charge 1. So the electric force exerted by charge 3 on charge 2 is bigger in magnitude than the force exerted by charge 1 on charge 2. Third, we find the x and y components of each electric force. So first we have F1 on 2, which is downwards on the vertical. So you must know that the angle is negative 90 degrees, as I already gave you in the 4 rules about the angles or the direction of a vector. The magnitude of F1 and over 2, we calculated it in the first step, is equal to 6.47 times 10 to the power 11 newtons. So in order to calculate the x component, we use the following equation. Rx is equal to r times cosine angle, equal to 6.47 times 10 to the power 11 newtons times cosine negative 90, equal to 0 newtons. Since this vector is on the vertical, then it doesn't have any x components. Ry is equal to r times sine angle, equal to 6.47 times 10 to the power 11 newtons times sine negative 90, and it is equal to negative 6.47 times 10 to the power 11 newtons. So all this vector, all the magnitude of this vector is on the y-axis and in the negative direction. Now force 3 on 2, it's equal to 2.99 times 10 to the power 12 newtons, and the direction is given to be 31 degrees. So in order to calculate the x component, we use the following equation, r times cosine angle. So 2.99 times 10 to the power 12 times cosine 31, it is equal to 2.56 times 10 to the power 12 newtons. And the y component is equal to r times sine angle, so 2.99 times 10 to the power 12 times sine 31, it is equal to 1.53 times 10 to the power 12 newtons. This is the third step. In the fourth step, we add the x and y components of the individual forces to find the x and y components of the total force. So the total force has an x component equal to Rx1 plus Rx2, which are the x components of force 1 and force 2. So it is equal to 0 newtons plus 2.56 times 10 to the power 12 newtons, equal to 2.56 times 10 to the power 12 newtons. And the y component is equal to the y components of force 1 and force 2. So force 1 on 2 and force 3 on 2. So it is equal to negative 6.47 times 10 to the power 11 newtons plus 1.53 times 10 to the power 12 newtons. And the answer is 8.83 times 10 to the power 11 newtons. Now we have the x and y components of the total force. Now in the fifth and final step, we need to find the magnitude and direction of the total electric force by drawing and by calculation. First, by drawing, look at the figure in the middle. In order to find the total electric force or the vector of the total electric force by drawing, we use the law of superposition that I already stated in this session. We draw the first vector, which is F1 on 2 as it is, negative on the vertical, so it is downwards on the vertical, and we put the tail of the second vector on the head of the first. So we put the tail of F3 on 2 on the head of F1 on 2. Then we draw the resultant vector, which is the vector of the total electric force acting on charge 2 from the tail of the first to the head of the last. As you can see in the figure, the total force is in green. Now by calculation, we find the magnitude and the direction of the total electric force using the equations of R and angle. We use the x and y components that we already found from adding the x and y components of the individual forces acting on charge 2. So R is equal to radical Rx squared plus Ry squared equal to 2.56 times 10 to the power 12 newtons squared plus 8.83 times 10 to the power 12 newtons squared equal to 2.7 times 10 to the power 12 newtons. This is the magnitude of the total electric force acting on charge 2. As for the direction or the angle above the horizontal, it is equal to tangent minus 1 into Ry over Rx. Tangent minus 1 is put on the calculator as shift tangent. Shift tangent into 8.83 times 10 to the power 11, which is the y component, over 2.56 times 10 to the power 12, which is the x component. So the angle or the direction of the total electric force above the horizontal is equal to 19.03 degrees. Now as a homework, please find the magnitude and the direction of the total electric force acting on charge 2 shown in the following figure. Q2 is equal to negative 10 coulombs. Q3 is equal to positive 11 coulombs. Q1 is equal to negative 15 coulombs. The distance between charge 2 and charge 3 is 0.7 meters, and the distance between charge 2 and charge 1 is 0.55 meters. In order to solve this problem, you need to follow the 5 steps that I explained in the example. So please be accurate and be clear in your answers. Your homeworks must be done and submitted to me on Thursday, April 16. Thank you, good luck, and stay safe.